This is the solution to the second problem for Friday, March 13th recitation. And in this problem, we confess we got our schedules a little bit messed up. We hadn't actually introduced what a watt is, or the idea of power, and the units that these things are measured in when you got to this recitation. Things were a little bit crazy on Thursday. So I'd like to do that now, and in the process do this problem. Um, so we talked in the previous problem about how the SI unit of measuring energy is the joule. So I'm going to just write a few things here. So whoop, I'm on the wrong color. There we go. So 1 joule is 1 Newton times 1 meter. Again, because it is a unit of work. Since we also measure kinetic energy in joules, since kinetic energy is 1/2 mv squared, you can also remember that the units of joules are kilograms meters squared per second squared, mv squared. Another unit, though, is the watt. You're probably familiar casually with watts as a rate of using energy, a rate of converting energy from one form to the other. So a light bulb, for instance, might say that it's a 20-watt light bulb, and that means that this light bulb consumes 20 watts of electrical energy every second and converts it into 20 joules every second and converts it into 20 joules of some other kind of energy. So 1 watt is 1 joule per second. If you care, this is also a kilogram meter squared per seconds cubed, although it's very rarely helpful to think of it that way. Let me fix that. I'm still learning how to use a tablet and stylus. There we are. So a watt times an hour so 1 watt hour is 1 joule per second times 1 hour. Now I have to convert an hour into seconds to cancel these. So obviously I have 2 units of time. Sorry folks, I am still learning to use my tablet. So this is a unit of time. Second is also a unit of time. So this is also, I'm just going to convert an hour into seconds here. 1 joule per second times 3,600 seconds per hour. And now I can cancel the seconds. So 1 watt hour is 3,600 joules. So I'm supposed to figure out how much 97 watt hours is. That's the capacity of a large laptop battery. So, whoops, that's not what I wanted. I wanted to draw in a different color. So 97 watt hours is, let me find my handy dandy little Python window to do math. 97 watt hours times 3,600 joules is what 1 watt hour is 349,200 joules. So that is an awful lot of energy. That's what's in a laptop battery, and that's why you have to be careful with things like laptop batteries when taking them on airplanes. Part B says, if a motor had access to this energy, how far could it lift something? So we're imagining, say, take all the computing hardware out of my laptop, put a little motor in, connect it to some wheels, and let it try to wheel itself up a hill. Now, we're not trying to accelerate the laptop, right? We're not trying to give it a very high final velocity. We're just imagining this crawling slowly up a hill at constant speed. So here I'm going to use the work energy theorem. So the work energy theorem again says that the initial kinetic energy plus the work done by all forces equals the final kinetic energy. The forces here are gravity and whatever the motor is doing. So this becomes the initial kinetic energy plus the work done by gravity plus the work done by the motor equals the final kinetic energy. And since I know that I'm not accelerating, right? The speed at the beginning and the speed at the end of this motion are going to be basically the same. I can cancel those things. So all that means is that the work done by gravity plus the work done by the motor equals 0. Now the motor is doing positive work. Gravity is doing negative work. Let's just remind us of this. Whoa, I have a button on my stylus that turns the writing orange, and it's hard to hold that button down and write well. So the work done by the motor should be positive. The work done by gravity we expect to be negative. The work done by gravity, again, it is moving upward, but the force of gravity goes downward. So here, the motion is up, the force is down. So the work done by gravity is going to be minus the force of gravity times the distance moved. And for the work done by the motor, this is just 349,000 joules. That's the part we found from part A. So putting those values in now, whoops, I have minus mgh plus the work done by the motor is 0. So this tells me that the height is going to be the work done by the motor divided by mg, and I know that the mass is 2 kilograms. So going back to my handy dandy little Python window, I need 349,200 joules divided by 2 kilograms times g. And this gives me an enormous height. So tabbing back here, this is 17,460 meters. Or to 3 sig figs, 17.5 kilometers. Yes, there is an enormous amount of energy stored in a lithium battery. So that is problem 2 from Friday, March 13th's recitation, along with a little bit of an introduction of the idea of power and the units of power and work and energy, which I unfortunately forgot to talk about in class the Thursday before spring break. We will make sure to catch that up next week. Thank you all.